Swayam Prabha. Digital India. Educated India.
So what we'll be doing in today's few classes and a little bit of tomorrow is giving you some brief mathematical foundation tools to equip you so that you can work with the remainder of the classes. So what we'll be doing is a very, very brief and quick foray into linear algebra and optimization. Now these are courses by themselves. So I'm going to pack as much as what is relevant and what I think is relevant into these couple of days of lecturing. Some of you may have seen several of these because I'm not going to be talking about something which you probably not have seen, linear algebra and possibly in optimization. But I'll also be trying to give you a very different, slightly different flavor, a more geometric flavor if you will. That is why I'm going to also be using the slide and drawing things as we go along. So why do we study linear algebra? We study them primarily because we help them to understand when equations can be solved, under what conditions you can solve them. So let's just take the simple example of a flow sheet here. What this means is, some material is coming here at a rate of Q in, and material is going out at the rate of Q out. And there are things which are happening within the system. Around any node, mass is conserved. So whatever comes in has to go out. So now there are, as you can see, 1, 2, 3, 4, 5, 6 streams or flow rates. And you want to know, at some times, you cannot possibly measure all of these streams. Suppose I told you that this flow rate was 5, and I'm only measuring the other outlet flow rate is also 5, which it has to be because inlet should be equal to outlet. If I asked you this question, can you tell me what are all the other flow rates? So obviously, whatever is going into 1 should go out of 1. So Q in this is also equal to 5. Now Q43 plus Q1, Q2, you could write that equation. Now you can write Q2 is equal to Q3, and again you can write Q3 is equal to Q out plus Q43. Now there are 3 equations, and you can also count how many number of unknowns are there. And just a quick in this case it's just a quick analysis or a quick glance at this will tell you that if I told you only what is Q in and Q out, you cannot solve for the others. Right? In addition, if I told you that this was 1, then you should be able to figure out what are the other flow rates. Right? So in these kinds, this is a very simple toy example which you can do the analysis by hand, by inspection. But what happens when you have a large number of equations, when you have large number of unknowns? It's typically common to have systems with thousands of variables, thousands of unknowns. And in such a case, how do you decide whether the information that has been given to you, whether it is sufficient for you to be able to solve? Secondly, if there is enough information, is it even consistent? Suppose on the other hand, I had told you that Q in equal to 5 and Q out equal to 6, and I gave you Q43 equal to 1. And then I asked you to solve for some of the others, you will find that there is something called inconsistency. I have given you enough information, in fact more information than what is necessary, and it turns out, however, that the information is not consistent. So what happens when this kind of situations occur? So these are some of the things. Can we first upfront recognize that these situations have occurred, whether there's enough information, whether there's no information, or if there's information, whether the information is consistent. So linear algebra helps us to get a handle of some of these things. Another kind of problems which we will also do today in the tutorial is, if I ask you, for instance, that let's say this is Goa and this is rest of India. Right? Now I ask you, and let's assume that the populations are stabilized. Goa is probably a state where the populations are stabilized, and let's assume the rest of India is not really growing it's not growing. So what I am saying is, that every year 10% of the people from Goa move out, and because Goa is a much 20% of people from outside Goa move in. Right? Now as I said, let's not talk about whether increase in number of people. It's only I'm going to ask, does the population ratios of people, does the population stabilize? And if it stabilizes, what is the steady state distribution of these populations? Roughly, what is the population, if I start with 1 lakh people totally, what is the distribution of people within Goa and outside and the rest of India? How does it change? Then how long does it reach to steady state, if at all it reaches steady state? So these are simple questions in dynamics, or as the name suggests, things are growing, right? And there are things are changing, not necessarily growing, things are changing, and how do you answer some of these questions? Again, this is a simple enough toy problem that you can write down these equations without recourse to linear algebra. You can write down the equations, you can, with a little bit of algebraic manipulation, you can solve them. But then as the systems become more and more complex, right? Now we know that we have a large number of states in our country, and we ask about people always moving in, moving out of the states, and we're going to ask questions about what is the steady state distribution population of the people in all these states. Then that's a large number of states, and those you don't have the, you need to have tools to be able to solve such systems. We are also going to see how you can do these things as part of the course. This is a course in data science, and I'm sure these kinds of concepts are going to be covered in much more detail and in much more rigor with the correct statistical underpinning by several of my colleagues later on. But I'll just introduce how linear algebra can be used to solve some of these problems. So, you collected data, you do experiments, you collected some data, and let's call this x and y. So, I'm not going to tell you what x and y are really, what are the sources and so on, what they represent, but let's assume that somebody has told you x and y are linearly related. So, you have y equal to mx plus c. And then you have gone and done an experiment, you collected some data, or you collected some data and you want to fit a linear model between the two variables x and y. Now, let's say linear model, this is indicated by some kind of one of these straight lines. Now, unfortunately, the dots over here are the data that you collected. In an ideal world, if you think the linear model is correct, or if the linear relationship is correct, in an ideal world, all of these data points should lie on the same straight line. However, life is not ideal. There is always going to be some kind of error. Somebody made an error, mistake in recording the data. Even after they recorded the data correctly, but it was transmitted incorrectly because it was sent over some communication channel, or maybe the real model is not linear. So there is always going to be some source of error. And as I said, my colleagues will be explaining to you what are these sources of errors and how you should address them in a very rigorous manner, but I'll just give you a very brief, it could be treated as a purely geometry problem. So I have several points over here denoted by the blue lines, and I want to find a line that best explains the data, or the so-called the best fit straight line, or the least squares estimate of the slope, and every line can, in 2 dimensions, it is parameterized by a slope and an intercept, the slope being m over here and c over here. So I have several data points. Now this is clearly a case in which if you want to fit a line in a plane, you need 2 data points, right? And therefore, any 2 data points you could fit a line. So I could fit a line like this, I could fit one of these lines, I could fit this line, I could fit this line, and so there are as many, you have n choose 2 possible straight lines that you could fit by taking any 2 pairs of points at one time. Obviously, some of these don't seem to make sense. It's very unclear. It's not clear that this kind of relationship is what you're looking for. It's more likely that you're looking for a relationship that is indicated by the dotted lines. So how do you discover this relationship? This is another set of questions that we will try to answer towards the end of the day. Okay, so to do these things, we need to have some formal definitions. So linear algebra, as the name suggests, looks like it's about algebra. And when you go back to high school, typically, especially, I don't know how it is today, but when we were in school, there was always, when we went to middle school, it was algebra and geometry. In algebra, you did things like you solved equations. You had variables, you had indeterminates, x, y, z, you factorized, you solved quadratic linear equations, then you solved quadratic equations. And geometry, it was all about starting with points, lines, planes, circles, figures, and so on. Now, the name linear algebra seems to suggest that there's a strong algebraic flavor in terms of variables, equations, and so on. However, it also has a very, very strong geometric flavor, and that's what I'm going to try and convey to you in this hour. So when you talk about algebra, as I said, you talk about equations, variables, how to solve them. Geometry is about points, lines, and planes. So to do linear algebra pretty much you can do very little thing, very basic operations. But at the same time, this is so rich that it gives rise to you can do many things just by doing 2 things. So to do 2 things, we need to first understand what are vectors. A vector, typically, I won't go into very, very rigorous definitions of what is a vector and what are things like scalars and so on. So you need to have 2 things, vectors and scalars. Scalars, you can think of them as, pretty much for all the purposes of this course is concerned, as real numbers. And vectors, you can take them off as ordered set of real numbers. So when I say an ordered set, it means the order in which you write them is important. Simplest thing is I will take an ordered pair. So I will just take an ordered pair x1, x2, and x1 is in the set of real numbers, x2 is also from the set of real numbers. And then I will have some scalars which are also coming from real numbers. So this is an ordered set, which means the order in which I write them is important. Now this is a very purely abstract algebraic construct. Right? There is no, I just written things down in a very symbolic manner. However, it has a very strong geometric interpretation that I can give you. The way I do that is, I take two lines, two perpendicular lines, and then I draw it on a plain sheet of paper like over here, and then let me call this the x1 axis and x2 axis. So any vector here which I have described algebraically as an ordered set x1, x2, I am going to try and show it geometrically. How do I do that? On this line, I start marking out, I take this point, I call this the origin, and then I start marking out in units of some whatever units you want. This is 1, this is 2, this is 3, and so on. Likewise over here, I can start marking out 1, 2, 3. So what I have done is, on this line I have started to mark out the natural numbers. On the other perpendicular line also started to mark out the natural numbers. Now I can go and start marking out negative numbers, and so on. Likewise on the other axis also I will start marking out negative numbers, and so on. Now from if you have natural numbers, you can also, if you go back to you can start constructing rational numbers. So I give any rational number which is a ratio of two non-zero two integers, as long as the denominator is not 0, I can start marking out. So if you give me a number say half, I can mark out over here. If you give me say 1.5 or 1.3, I can mark them out. Now I can extend this to non-rational or irrational numbers also. I can pretty much mark out all the real numbers on this axis and on this axis. So if you give me a vector over here, an algebraic and a very purely algebraic creature, an ordered set of two real numbers, I am now, because these are real numbers, and I know how to, I have marked out all possible real numbers on this line and on this line. So if you give me any real number, any vector over here, let's say 0, 1, it's an ordered set. Give me that. I will try and I will mark it over here. So which means this is the point 0, 1. So this is a vector over here which is defined purely algebraically as an ordered set. I have now marked this as a point over here. In high school, we also try to mark vectors as directed ray starting from the origin and ending at the point. So it's much more nicer to visualize these vectors with a tail and a head, or you could just mark a vector as a point. Likewise, if you give me a vector say 3, 2, I just go 3 on this x-axis over here and 2 on the perpendicular axis, and then I mark this point over here. This point itself is a geometric representation of the same algebraic thing vector. To be more fancy and clear, to be more figurative, I can show it to you in a vector having a head over here and an arrowhead over here. So now this is pretty much how we try to visualize vectors. So when you want to think about an abstract sense vectors, I can think about them as representing some points in space. So in this case, these are two-dimensional vectors because this is an ordered pair. I could give you, an ordered set of 3 real numbers, and then it would represent a plane. It would represent a point in 3 dimensions. Of course, I can extend this. I can give you an ordered set of 4 real numbers, and this will represent a point. However, you cannot visualize this. You can just have to imagine, take a leap of imagination, and then visualize this as a point in 4-dimensional space. Something that we cannot visualize or appreciate it. But a vector which is represented nicely as an ordered set of 4 real numbers over here, you can think of it as representing really a point in higher dimensional space. So that is the first connection between vectors and geometry, because a vector can be used to represent a point in some space. Now, as I said, there are 2 basic operations that you can do with vectors in vector spaces. If you have a vector, let's say this vector x1, x2, and a scalar, I can multiply a vector and a scalar. This is how it is defined. This is a vector and the scalar. The scalar multiplication of vector by alpha, the vector is given by alpha x1 and alpha x2. So what does this mean geometrically? Let's take this example, a very simple example over here, say 1, 1, the vector 1, 1, and then this is where it probably is. Now if I want to multiply it by a scalar, let's take simple example of alpha equal to 2. What happens to it? If I multiply it by, if I take 2 times this vector, I get 2 comma 2. Geometrically what happens to it? I get another vector over here, you get over here 2, you mark out 2 comma 2, and then this is my first vector, and after multiplication I get another vector. In this case you can see multiplication of a vector by a scalar does not change direction, it only it does in some sense you get a new vector which is collinear with the old vector. So when I say doesn't change direction, I'll maybe slightly abuse notation. If I had multiplied it by minus 2, I would have got minus 2 comma minus 2. In this case I get a vector. Of course it has flipped all the way around, but in some sense it is still collinear with the old vector. So as if you are ready to ignore that it has completely flipped directions, if I say the two vectors which are in opposite direction, which are pointing seemingly in opposite direction, but they are at least collinear. So what has happened is, with scalar multiplication of vectors gives you another vector which is still collinear with the old vector. Now these scalars have to come from certain, scalars, in this case they come from real numbers. They have to satisfy certain properties. Scalars could be positive, it could be negative, it could be rational, irrational, but definitely also has to include the 0 number. So if I multiply a vector by 0 scalar, I get the origin 0, 0 over here. Now, the other operation that I can do with vectors in vector spaces is vector addition. So that's easy again to define it in an algebraic manner. Suppose I have a vector which is denoted by x1, x2 and another vector y1, y2. Vector addition algebraically is very easy. We just add it column wise or component wise. So this is x1 plus x2, this is, sorry, so this is x1 plus y1 and x2 plus y2. So let me try and clean some of this over here. So vector addition in if you want to think of it geometrically is also very, we have done this in high school. So this is my vector x, the first vector, and this is my second vector. This is x1 comma x2. This is say y1 comma y2. So now how do you realize this? You remember the law of completion of the parallelogram. You extend this parallelogram, and this is my resulting vector over here. You can verify this is what it happens. What you are doing algebraically when adding component wise, what you are doing geometrically is completing the parallelogram and looking at the diagonal. That is your resulting vector. This is something which we have seen in high school physics. The same thing can be done in 3 dimensions. In higher dimensions also the intuition is the same. However, we cannot visualize parallelograms or vectors or points in higher dimensions. So vector space pretty much, so what are all the things? So you can also do, as I said, you can do 2 things, as I said, scalar multiplication, vector addition. So vector spaces have to satisfy certain fundamental properties, which is that when you take a vector and multiply by scalar, you should continue to get a vector. The resulting object should be a vector, which means if you take it should be another point in the space over here. If you take 2 vectors and add them, it should be the third thing that you get should also be a vector. So the vector, you should be able to draw the other new point also in this space over here. If any of these properties is not satisfied, the collection of your objects is not a vector space. Now, and the way I have defined this, if I take ordered set of real numbers and my scalars I take any real number, then it satisfies the axioms of a vector space. What that means is it is closed under vector addition and scalar multiplication. You add 2 vectors, you should continue to get a vector. You take a vector multiplied by a scalar, you should continue to get a vector. So now what about, suppose let me call the 2 vectors, let me call vectors v1, v2, right. Now what can you say about alpha v1 plus alpha v2? What should it be? It should also be a vector, right? Because alpha v1 is a vector, alpha v2 is a vector, alpha v1 plus alpha 1 v1 plus alpha 2 v2 is also another vector. So what is that happening geometrically? If this is my vector v1 and this is my vector v2, alpha v1, maybe it is some vector like this, and alpha v2 is another vector like this, alpha 2 v2 is some vector like this, and alpha 1 v1 plus alpha 2 v2 would be, I would have to construct this parallelogram and draw this vector. So if you go back to if you recall what maybe you would have done this in a course in linear algebra formally, they ask you to verify whether, if they give you certain collections of objects and ask you to verify whether it's a vector space or not, it's very easy to verify them very mechanically. You take arbitrary linear, you take a scalar multiple of a vector, another scalar multiple of another vector, and add them and see whether you continue to get a vector. If it continues to satisfy the original properties of how you defined a vector, then it is indeed a legitimate and a valid vector space. For all practical purposes, at least as far as this couple of hours are going to be concerned, we will be talking about vectors which are two-dimensional vectors which are created by points in the space, and scalars will also be real numbers. However, it does not mean that vector spaces have to be built only from these. You could build them from various other objects. Scalars you could build vector spaces from other objects which are sometimes very abstract. However, for all practical purposes, especially as far as this course is concerned, we will be satisfied to working with real numbers, ordered sets of real numbers, and scalars as real numbers. Okay, so what can you do with vectors? You can pretty much, there's very limited things you can do. You can take vectors, multiply them as scalars, and add two vectors. So if you give me n vectors, right, they could all be distinct. They could be, suppose I give you n vectors, when a1 is a vector, a2 is a vector, an, each of this is a vector, and I give you n scalars also, alpha 1, alpha 2, alpha n. This is called a linear combination. Alpha 1 a1 plus alpha 2 a2 all the way up to alpha n an is called a linear combination. Now some of these vectors, now these vectors are called linearly independent when if and only if. So you can take these linearly independent, take these vectors, take linear scalar combinations, and then try to find a linear combination that sums to 0. First question is, can you always find a linear, if I give you any vectors, can you always find a linear combination that sums to 0? Yes. That is a so-called trivial combination. I choose all the scalars to be identically 0. So you give me any vector, any set of vectors, I can always make a linear combination that gives me the 0 vector by just taking the vectors to be, the scalars to be 0. Now, however, if I give you a set of vectors and let's say I give you these two vectors, right? Let's say this is 1, 1 and this is say minus 1, 1. So I have the vector 1, 1 and minus 1 and 1. So I am going to ask you, I can take the combination of these two vectors and then I can make them the 0 vector. That is possible. I just take alpha 1 equal to 0 and alpha 2 equal to 0. Now, is this the only possible way I can get a 0 vector from these two vectors? In this case, it turns out yes. That is, the only solution, only way I can get the 0 vector is by choosing alpha 1 equal to 0 and alpha 2 equal to 0 for any other value of alpha 1 and alpha 2. No matter how small, how big, how positive, negative, very large, very small, I will never, if I choose both, I will never be able to get identically the 0 vector for any other choice of alphas or scalars. And why is that happening intuitively? Intuitively it is because they are pointing in two different directions. Intuitively, that's not completely correct. Intuitively, that's pointing out in two different directions. In 2 dimensions, that is correct. They're pointing in two different directions, and therefore they are called independent vectors because I cannot find a combination, a linear combination that gives me the 0 vector, except the trivial solution. So in this case, these two vectors are independent vectors. Now, if I take these two vectors, right? Let's take 1, 1 and 2, 2. Now, these vectors are dependent vectors because as you can see, one is a scalar multiple of the other. Or another way is, how do I find a non-trivial combination that makes them the 0 vector? Very simple. Minus 2 times 1, 1 plus 2, 2 gives me 0, 0. So this is a non-trivial combination of these two vectors which gives me the 0 vector. And in this case, they are dependent vectors because they are, in this case also happens because they are pointing in the same direction. And you can find a non-trivial combination of these two vectors that gives me the 0 vector. So what this means is, the two vectors, in this case the two vectors were independent, here the two vectors were dependent. Now when you want to give a more general definition of these dependent and independent vectors, this is the correct formal definition. I will say a set of vectors are independent if and only if the only solution to this kind of an equation is the trivial solution, that is the alpha, all the scalars are equal to 0. It does not mean that the vectors have to point in 2 dimensions. It happens when the vectors are pointing in the same direction. In 3 dimensions, it's possible that the vectors are pointing in different directions and yet they are linearly dependent. How does that happen? You take 3 vectors in a plane. All the 3 vectors are lying in the plane. Right? I'm not. All the 3 vectors are lying in the plane. They are all pointing in different directions and yet they are linearly dependent. How? Because I can always write one vector as a linear combination of the others. I don't know what those scalars are, but I can find non-trivial combinations, non-zero combinations, such as I can write one vector as a linear combination of the other 2 vectors. So in this case, these 3 vectors are linearly dependent. So it does not necessary that they have to just point in the same direction for them to be linearly dependent. As long as I can find a non-trivial combination of these vectors which sums to 0, then the vectors become linearly dependent. So let's clear this slide. Now, given a vector space, there are obviously infinite number of such, it's possible that there are infinite vectors. Now I will try to find the largest set of independent vectors such that every other vector can be written as a linear combination of these 2 vectors. That's called a basis set. So for instance, in the plane, this is a very typical example of a basis set vector, the so-called unit vector, the standard vectors. This is 1, 0, the point 1, 0, this is a point 0, 1. So if you give me any vector x, y, I can obviously write it as a linear combination of these 2 vectors. Right? You give me a point here 5, 2, 5, 3, this is equal to 5 times so in these 2 vectors are linearly independent. Clearly they are pointing in different directions, and we know that we cannot write one vector as a multiple of the other. They are linearly independent. Any other vector can be written as a linear combination of these 2 vectors. However, this is the standard or the most intuitive choice of a basis set. However, this is not the only choice. I could take any 2 set of independent vectors. In the plane, we know that any 2 non-zero vectors which are pointing in different directions, they are basis vectors. So I could take this as one basis vector and this is another basis vector, and any other third vector can be written as a linear combination of these 2 vectors. Right? That's obvious. You give me a vector like this, I just have to, if you give me this vector, I just write it as a linear combination of this plus this. So you give me this vector over here, I just do a similar thing, I draw the parallelogram on the other side, and then I find linear combinations such that one vector can be written as a linear combination of the other 2. So the basis in some sense is useful because it helps you to represent any arbitrary vector as a linear combination of this. Plus, most importantly, that combination is unique. So for instance, in this case, x, y is equal to there is no other combination which will give me of 1, 0 and 0, 1 which will give me the vector phi 2. This is obvious when the vectors are the standard basis vectors. For any other arbitrary basis set of basis vectors also, this property holds that every other vector can be written uniquely as a linear combination of these 2 of the basis vectors. That is important, that it should be able to write it uniquely as a linear combination of the basis vectors. Now let's go on to other next most important thing that we would like to work with, matrices. So what is a matrix? A matrix really represents, you can think of it as represents linear transformations. So for instance, if I give you this matrix, what it tells me is it is taking 2-dimensional vectors and giving me 3-dimensional vectors. So let me tell you what it means. Suppose I say I take a vector 1, 0. Right? I take, what this matrix does is, I know how to do a matrix multiplication. So what this does is it basically takes this matrix takes this vector 1, 0 and gives me it gives me a vector 2, 1, 0. Now I can take any other vector. What would this be? 0, 4, 1. Now, if you noticed, the columns are what? The columns, as I said, let's say the original basis vectors are 1, 0 and 0, 1. Now, the columns of the matrix are basically telling you what happens to these standard basis vectors after the transformation. So you say the first column was, if you ask me what happened to the vector 1 0, it was the vector 2 1 0. If you ask me what happened to the vector 0 1 after transformation, it was 0 4 1. So the columns of the matrix are basically telling me what is happening to the vectors after transformation. So in this case, what this matrix does is it takes vectors from 2 dimensions and gives me vectors in 3 dimensions. That is perfectly possible, and that is perfectly allowed. You can take vectors from 2 dimensions and give me vectors in 3 dimensions, or it could be converse, it could take vectors from 2 dimensions and give me vectors in 3 dimensions. But the columns of the matrix are basically telling you what is happening to the standard basis vectors on transformation. So this is an important idea that we need to keep in mind. So if this was a 2-dimensional vector, if the 2-dimensional matrix 2 0 1 4, what this would mean is, if I told you what is this vector, the standard basis vector becomes 2 0 after transformation, the standard vector 0 1 becomes 1 4 after transformation. And any other vector, if I ask you what happens to it on transformation, I know how to do that. Suppose I ask you what happens to a vector 2 0 1 4 times any other vector x y, we know how to do that. It is just 2x and x plus 4y, or it is just x times 2 1 plus 4 times 0 4. So y times 0. So what the matrix is doing is, it is transforming vectors from one space to another space. It is taking, and the columns of those matrix are basically just what are the vectors that you get on transforming the standard basis vectors. So you take the standard basis vectors, transform it one at a time, the columns of the matrix will tell you what is happening, what has happened to the resulting vectors. Now matrix, as I said, could be from 2 dimensions, 3 dimensions, 3 dimensions, 2 dimensions. A square matrix is a very special class of matrix because it takes only 2 dimensions. It takes a matrix is square if the number of rows is equal to the number of columns. So this is M and this is N. So if M equal to N, it's a square matrix. So what it means is it takes an n dimensional vector and it gives me an n dimensional vector. So for this, you can ask this question. Suppose I take this vector over here. I take this matrix 2 0 1 4, right. So this is what was the original, let me call this is 1 0 0 1. So in this case, let me call this a unit cell, the first square that is formed by these two standard basis vectors. Now after transforming by this matrix, let me call this matrix A over here. After transforming by this matrix, I get 1 0 becomes 2 0 and 0 1 becomes, oh sorry, this was different. 1 0 has become, 2 1 and 0 1 has become 0 4. Now if you ask me, in this case the initial volume of the unit square was, area was 1. Now I can ask you what is, now after transformation the unit square has become a parallelogram. Now I can ask you what is the area of this parallelogram after transformation. You could use coordinate geometry or simple geometry and formula to compute it. It turns out that this can also, if you all of you are familiar with determinant and definition of determinant, so I won't go into that. But in this case, the absolute value of the determinant is equal to the volume of this parallelogram after transformation. And the reason I am giving you this is because of geometric interpretation, which you may not have seen before. The determinant is the volume of the parallelogram that you get after the unit vectors have been transformed. In the absolute value, determinant will be positive or negative, but if you take the absolute value of the determinant, you end up getting the area. In this case, in 2 dimensions is the area, in 3 dimensions is the volume of the parallelepiped, and high dimensions again it's some notion of volume, but it's something which we can't obviously touch or feel and experience. Now this is important. This is again there are several properties of determinant which some of you may know, which you have used in a lot of these things, but we will use one of these properties about singularity of determinants. Now determinant obviously is defined only for singular matrices, for square matrices. Determinant is not defined for rectangular matrices. Determinant is defined only for square matrices. Now a matrix is singular. If we define that a matrix is singular, determinant is 0. Now geometrically, what does it mean? Algebraically, we know we can calculate, expand the determinant and so on and show that the volume is determinant is 0. What does it mean to say geometrically when the determinant is 0? So in this case, determinant was 8 and the volume of the parallelogram or the area of the parallelogram was, we can calculate and show that it is 8 units. Now let me clean up this over here.